As promised, I have a video on forces and using Newton's second law for you guys. This is going to be the first of two videos, and this one will be a tension problem. So, you can see the problem statement right here. We have a sign with a mass of 8 kilograms hanging from two wires with angles of 40 degrees from vertical and 20 degrees from horizontal, and we want to determine the tension in each wire. Tension is definitely a force, so this is going to be a forces problem. And in any forces problem, one of the first things we need to do is identify the forces that we have and draw a free body diagram. So, the sign has a mass that's given to us, so that means our sign will have a force of weight, and the force of weight acts straight down. The force of a wire or a rope is the tension, so each one of these ropes will have their own tension force. I'll call this one tension 2 to go along with theta 2, and I will call this one tension 1 to go along with theta 1. So, to kind of redraw our free body diagram with all of our vectors connected, we then have T2 acting up and to the right, where this angle is our 20 degrees. And we have T1 acting up and to the left, where this angle from the vertical is our 40 degrees. And we have the force of weight acting straight down. In any F equals ma problem, once we've got our free body diagram, we're ready to start writing our equations. So, it doesn't really matter whether we start off with the x or y direction. So here, let's just start off with the x direction. The equation we want to write down when we're showing our work is the sum of the forces in the x direction equals the mass times the acceleration in the x direction. Whenever we write this equation, we have some steps that we follow. On the right-hand side of this equation, the side that says ma, all we have to decide is the acceleration 0 or is the acceleration not 0? This sign is hanging there and is presumably at rest. So whenever anything is at rest, it has an acceleration of 0. Then we come over to the left side of this equation here, and we want to fill in our forces from our free body diagrams, putting appropriate positive and negative signs in there to indicate direction, and taking any vector components we need to. So we can kind of go through our forces one at a time to see if they have any x components. The weight points straight down. And assuming we're working with the coordinate system we normally do, my bad, I should have put that up there before, the weight has no x component. Tension 2 does have an x component though, and so does tension 1. So we will want tension 1, but not the whole thing, because not the whole vector points in the x direction. We just want the x component of it, so I'll just put a little x for now. And the x component of tension 1 points to the left in the negative x direction. Then we'll also have the x component of tension 2 pointing to the right. And that's it as far as the x direction is concerned. So now we can bust out our sines and cosines to help us here. With T1, the x component is the opposite side of the triangle, and opposite goes with sine. So negative T1 sine of 40 degrees is our x component of tension 1. And then for tension 2, the x component is our adjacent side. So we want T2 times the cosine of 20 degrees. And that all still equals 0. So, that's our F equals ma equation for the x direction, and you might notice that we have two unknowns. We don't know T1, and we don't know T2. So this equation by itself won't help us solve for anything. So we know for sure we're going to need another equation. So, If we've already tried our x equation, a good next step would be to try our y equation. The net force in the y direction equals the mass times acceleration in the y direction. Again, same steps whenever we use this equation. On the right-hand side, our acceleration is 0, so we set the right-hand side equal to 0. Then on the left-hand side, we fill in forces from our free body diagram. Tension 1 does point in the y direction, but not all of it. Just a component of tension 1 points in the y direction, T1y, in the positive y direction. So positive T1y is one of our y forces. Similarly, tension 2 also has a y component, T2y, that also points in the positive y direction. So we will add T2y to our y equation here. And the weight vector is also in the y direction, and the entire weight vector already lines up with our y direction, so we don't need any components here. We do, however, need a negative sign because the weight points down. Now we're ready for any sines and cosines and formulas we might need. So the y component of tension 1 is the adjacent component, so that goes with the cosine of 40 degrees, T1 cosine 40. The y component of tension 2 is the opposite component to that 20 degrees. So we want positive T2 times the sine of 20 degrees, and then minus the weight, so minus mg, all equals 0. Again, we have two unknowns. But we have these same two unknowns. We know all of our angles, we know m, we know g. So if we have two equations and two unknowns, that means we can solve for both variables with a system of equations. So I'm going to do all of my systems of equations work over here on the right side of the page. We've written our F equals ma equations, and we know we have enough equations for the number of unknowns we have, so after this, it's just math. So, to solve a system of equations, we take one of our two equations and solve it for one of our unknowns. So first I'm going to rearrange this equation here, adding the T1 sine of 40 degrees to the opposite side. So we have T1 sine of 40 equals T2 cosine of 20 degrees. And we want to rewrite this equation so that we have one of our unknowns by itself on one side of the equation. So I'm going to solve for T1. T1 will equal T2 times the cosine of 20 degrees divided by the sine of 40 degrees. Now, if we want to, right now, we can take that cosine of 20 divided by sine of 40 and just replace it with a number, because we know those angles. So T1 equals T2 times 1.462. Or written a different way, T1 equals 1.462 times T2. So this equation will help us out here, because now we're going to take that and plug it in to our other equation. So our second equation, the first thing that happens is T1. So instead of T1, I'm going to put in 1.462 times T2, because that's equal to T1, times the cosine of 40 degrees, plus the rest of that equation. T2 times the sine of 20 degrees, minus mg, so minus 8 kilograms, times 9.8 meters per second squared, not negative, we've already accounted for the direction, equals 0. So now we just need to combine some like terms. So combining multiplying that cosine 40 by the 1.462 gives us 1.12 times tension 2. And sine of 20 is 0.34. So we have plus 0.34 T2 minus 74.8 newtons, which is our, sorry, my bad, 78.4 newtons, which is our weight, equals 0. So rearranging this, combining my like terms for T2, I have 1.46 times T2 equals 78.4 newtons, which I can solve by dividing by 1.46 and get T2 equals 53.7 newtons. So there's one of my tensions. Then, to finish off this problem, I just now need to plug that T2 back into any other equation I want that has both T1 and T2 in it. I could use this equation. I could use this equation. But the one I circled up here is the simplest one, so that's the one I'm going to use. T1 equals 1.462 times T2. So that's 1.462 times our 53.7 newtons, which gives us T1 equals 78.5 newtons. And now we have both of our tension forces. So we had to draw our free body diagram, choose a coordinate system, and set up our F equals ma equations. Once we did that, we realized that each equation has two unknowns, so neither equation can help us by itself. But since we have two equations and two unknowns, we can solve a system of equations. Solved one equation for one of our variables so that we could plug it in to the other equation. Then once we solved for one of our values, we plug that value back into any other equation to solve for the other unknown. That is it for this problem. Make sure you keep an eye out for the second video as well. That should be posted relatively soon.